Going live on YouTube. Live on YouTube. YouTube, is it live? Live on YouTube. Are we live on YouTube? Live on YouTube. I think we're live. All right. Testing, testing. How's it going? Sarah, 2ARX, Christopher, and Ishan. Testing, testing. How's it going? Sarah, 2ARX, Christopher. All right, this is definitely working. All right, and now we just got to wait for X to go live, and then we'll get started. All right, I think it's live on X. Let's make sure the volume is working and then get the stream started. How's it going, Ed? It's going, Max. All right, I think it's live on X. All right, perfect. It's working on all of them. Let me spit out this gum. Take a sip of water. How's it going, Max? Lil Kim, how's it going? Or is it Lickum? Can't even really see it. All right, let's start. Welcome, everybody, to another Hoopo stream. We're going to be trying to do two papers today, because both of these papers are not super complicated, so I figured let's do two of them, and they're related in a way. So this stream is called GSM1k and VLM Eval. We're going to be doing, this is the paper that I called VLM Eval. It's actually called VFC, Visual Fact Checker, but it's basically an evaluation paper for vision language models. So this paper came out 30th of April 2024, so really recently. This is coming out of NVIDIA, which is your favorite GPU manufacturer, but they also do a bunch of in-house machine learning work, so we're going to see what they have to do there. And then the second paper we will be looking at is called, it's actually a careful examination of large language model performance on grade school arithmetic. What this really is the GSM1k paper. So it's a paper released by Scale AI where they release a benchmark. So two different evaluation papers, and we're going to start with the NVIDIA one. All right. So in this paper, they are going to be presenting Visual Fact Checker, or VFC, which is a flexible training-free pipeline that generates high fidelity and detailed caption for both 2D images and 3D objects. So this is a pipeline, which is a bunch of models put together in some kind of engineered way that outputs captions, right? So the point is that you're going to give it a picture and it's going to output this text, which is the caption. And here in the kind of figure in the very front of the paper, which is usually the best figure in the paper, they're going to put it in the front page. You can see here they're comparing directly to GPT-4v, which is the state-of-the-art vision language model, is GPT-4v. But in this paper, they're going to show that by composing a bunch of open source vision language models and large language models and some object detection models, they're going to be able to kind of recreate or be on par with the GPT-4v. And the 3D is a little bit of a gimmick, but basically anything that you can apply to a two-dimensional image, you could take a three-dimensional object and have multiple views of it, which are just two-dimensional images, and then use the same exact pipeline. So they just kind of extend it a little bit to 3D as well. There is no explicit kind of 3D stuff going on in this. All right, so VFC is going to consist of 3 steps: proposal, verification, and captioning. We're going to go into those later when they present those. And the secret with this paper is that even though it's about VFC, really this paper is about evaluating vision language models. And you have to kind of get into the paper to realize this, but I think that's actually the strongest part of this paper, is the comprehensive captioning evaluation that they do. using 4 different metrics, and including a new metric that they propose here, which is going to be called clip image score. So, as I said before, state-of-the-art open source, which is comparable to the proprietary model of GPT-4V. Okay, Max recently went to a Star Trek conference. It was held at AMC Theaters. They rented out the whole place, had a lot of different presentations on the screen. Your contributions would have been dope to see. I don't know anything about Star Trek, Max. I think you might be confused. I'm in no way related to Star Trek. Maybe I'm wearing the red shirt. I guess the red shirt is like the engineering shirt. I'm more of a Star Wars guy than a Star Trek guy, but you know, I'm okay with all sci-fi fandoms. All right, let's get into this paper. Image captioning is about encapsulating visual data with a textual description, which requires a nuanced understanding of both modalities. The modalities here they're talking about is the modality of text, which is usually the domain of large language models, and then the modality of images, which is the domain of classically things like segmentation models, object detection models, but vision language models kind of bridge those together. Okay. There's still significant challenges with vision language models, such as overly succinct captions that neglect essential visual information. So basically the caption is too small, it doesn't really capture everything that's in there, or the opposite problem, which is hallucination, which is where you produce these long descriptions and sometimes your language model and your vision language model are just describing things that don't actually really exist in the image. So you're hallucinating fake details, right? So maybe it sees the birthday balloons and then it assumes that there's a birthday cake, because generally if there's birthday balloons, there's birthday cake, but there actually isn't a birthday cake in this image, right? So that's the hallucination problem. So VFC is going to be a training-free pipeline. So what do they mean by that? What they mean by that is that they're not going to be pushing any gradients. You know, they're not going to be fine-tuning a model or training a LoRa or doing anything like that. What they're going to be doing is creating a workflow or flow engineering, right? So if we actually scroll down to this figure here, you can kind of see what's happening here, where this pipeline is composed of multiple different models that are organized into this graph, right, where information flows from one into the other. There's some loops in here where the output of one model is fed into a different model, and ultimately you run this pipeline and you end up with your text caption. And I think this presents kind of the modern future of where we're going with these open source models, especially models that are on different modalities. And to kind of highlight what I'm talking about here, I have a tweet from Andrej Karpathy himself where he talks about prompt engineering, or rather flow engineering, intensifies for code generation. Here he's talking about Alpha Codium paper, which we actually have a stream on if you're interested in. But great reminder of how much alpha there is, aka how much signal there is, aka how much benefit there could be in moving from a naive prompt answer paradigm to a flow paradigm where the answer is constructed iteratively, right? So Andre here is letting you know that there's more alpha to be gained by doing these kind of flow engineering situations where you're using multiple models in conjunction with each other, where the output of one is being fed into another, as opposed to just a naive prompt answer where you're just kind of, here's the input is the image, and then here's your output, which is the text, right? So moving into these flows and engineering those flows, which is called flow engineering or workflow engineering or pipeline engineering. There really isn't a specific name for it because it's a very new technique. That's where we should be really looking at to drive performance, right? And this paper is kind of an example of how to do that. So that's going to be the first part of the paper, and the second part of the paper is going to be this evaluation where they're going to show their new metric, clip image score, and clip image score is going to be compared against clip score, GPT-4V, and then also human study. So human study is where you actually have a human that is evaluating the quality of these captions, such as this. So Amazon Mechanical Turk is a service that Amazon offers where basically you can pay to have people who sit there all day on these on this website and just click on things, and this is what they see. They see this image, they see two different captions, and they have to pick caption A or caption B. Right? So that's kind of the gold standard for quality detection, right? Is having a human check it, but maybe not, you know? And this paper did change my opinion a little bit, right? So I feel like one thing that is important is that you should be changing your opinions as you get more information, right? If you're listening to someone and they never change their opinions, they probably aren't being very scientific. And in my case, I used to be of the opinion, and you might have heard me rant time and time again on previous streams, that human evaluation is kind of the only way to evaluate quality. But in this paper, they introduce some new metrics, and then they show how those metrics are very correlated with human evaluation and possibly even a replacement for human evaluation, which would be really great because human evaluation is expensive, right? Amazon Mechanical Turk is expensive. If you're NVIDIA, that's totally fine. You can pay for that. But if we could figure out some automated evaluation methods that give you a very precise metric, such as clip image score, that would help research advance because then you could run evaluation very quickly and very cheaply. So, promising stuff coming out of this paper. Max Molly, it's an IT conference. Ah, okay, so Star Trek is not a Star Trek conference, it's an IT conference. Sashmit reminds me of some of the abstractions offered by DSPy. Yeah, that's the second time someone mentions DSPy on these streams. It seems like you guys are into that. I don't really use it, but it seems like everybody's using that. Okay. Let's keep going. So the pipeline is pretty simple, right? We don't really have to go through it. It's not complicated to explain. Let me just explain this pipeline. So you start off with a proposal, which generates an initial caption. So you're going to start off with a vision language model, such as Llama or Cosmos 2, right? So you're going to start, here's your image. You're going to have Lava, which is kind of a pretty standard open source vision language model that is a combination of a Llama, which is a large language model created by Meta. That's where the Lava comes out. And then the VA comes from VQA or visual. So it's basically a VLM, which is an image encoder that's plugged into a Llama model. But they're going to use two different ones here. So they're going to use Lava and Cosmos, right? And the reason you want to use multiple models is because different models bring unique perspectives, encompassing a broader range of information present in the image. So the more nitty-gritty explanation here is that different models are trained on different data sets, so they kind of have a different way of compressing information and a different way of what they extract in terms of semantic information from an image is going to be slightly different, right? So Cosmos has been trained on slightly different data. It's probably using a slightly different vision encoder. It's probably using a slightly different language model. It's been trained for slightly different amounts of time, different situations happening, that the caption that's going to come out of Lava and the caption that's going to come out of Cosmos are going to be different. Okay, so those two initial captions, you're going to feed them into a large language model. That large language model is going to be either GPT-4 or Llama 2. Obviously, if you want a full open source flow, you're going to be using Llama 2. And that language model is going to summarize the initial detailed descriptions, identify all the objects that could be verified, and then summarize it in an object checklist. And then you're going to have an open vocabulary object detection model, such as the segment anything model from Facebook. Open vocabulary means that it's a segmentation model or an object detection model that is not limited to a specific set of categories, right? Usually a detection model, classically, for example, trained on ImageNet, would only be able to classify or detect objects that are part of the original ImageNet categories, right? But an open vocabulary object detection model, which is something like the segment anything, it has already been trained in such a way that it's not limited to those categories, and it's just going to output open vocabulary, aka any kind of random stuff in there. So you're taking your captions from your open source VLMs, you're feeding them into a Llama 2. The Llama 2 is basically saying, okay, here's all the different objects that could exist. I'm going to run that, create a little object checklist of all the objects that exist in that, pass that into the object detection model. The object detection model is not actually consuming those, but it's detecting things, and then you're comparing the results. You're saying, okay, here's all the objects that I thought existed. Here's the objects that our open vocabulary detection model is saying, and I'm going to basically run this loop over and over again, and then basically try and curate or clean up the caption. So you're trying to get rid of the hallucinations or add any additional objects that might not have been captured by the original thing. Right. The LLM plays the pivotal role as a brain, refining and revising the initial captions, transforming them into final versions that are both coherent and richly detailed. So relatively simple workflow, right? You just have basically 4 different models here. Of course, you could use an ensemble of detection models. You could also probably use multiple language models. And those are the little knobs that you have available when designing these flows. They do a very similar thing for the 3D, right? You're basically just taking multiple views of a 3D object and then basically doing the same thing. Okay. Follows a similar structure. The 3D, you take multiple views, and then for each view, we have the same 3-step approach. In this case, they're using Lava 1.5 and Instruct Blip, so slightly different VLMs. Rather than enumerating potential objects, we employ the LLM to generate 5 critical questions, and then we utilize a VQA model, specifically Lava 1.5, to respond to these questions. So very similar, but rather than having an open vocabulary object detector, they have just a VQA, which is effectively kind of like a captioning model, except the captioning model consumes image tokens and then outputs text tokens. A VQA model will consume image tokens and text tokens, which represent some question, and that question is being created by the LLM, right? Okay. So that's pretty much the model, or the flow, right? And I think now we go back to Karpathy's tweet here where he's talking about a flow paradigm and maybe taking a step further, right? So really a way of describing what this is this idea of Socratic models, right? So Socratic models refers to this May 2022 paper from Google called Socratic Models, where you compose zero-shot multimodal models, right? So zero-shot means you're not training these in any way, you're just deploying them and you're combining them, right? So Socratic models, a modular framework in which multiple pre-trained models may be composed in zero-shot, aka the whole idea of flow engineering. But why is this interesting, right? And this all boils back down to the Socratic method. The Socratic method is based on this guy Socrates, who's a famous ancient kind of philosopher, logician kind of guy. And the Socratic method is really what it means is that you can, if you were constrained inside a box, right, that you had no external input, could you improve your thoughts? Basically, can you get smarter by just sitting there and kind of talking to yourself, right? And the answer to that is yes, that you can actually kind of do that. And where does this all lead? So here I have a tweet by Andrew Ng. It's a pretty long tweet, but the important part of this tweet is inexpensive token generation, blah, 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 agentic workflows. Pre-training an LLM on its own directly generated response to prompts doesn't help. But if an agentic workflow implemented with the LLM results in higher quality output than the LLM can generate directly, then training on that output becomes potentially useful, right? So we've done a bunch of these streams on self-play loops and synthetic data. How do you generate better data so that you can train your model on that better data and then make a better model, right? If you just take your vision language model and you just caption a bunch of new images and then train on that, you're not going to necessarily make a better model, right? You're just kind of generating data that's already at the level of your model. But if you can create a workflow such as this that allows you to use weaker models in order to create a caption, and this 2D caption right here is better than the caption that would be created by one of these models, then what you can do is take that caption, now use it as the label for this image, and you've now created a flow which allows you to create higher quality data, and that higher quality data will allow you to create a better captioning model. And then that better captioning model, you can plug it back into your flow and then do it again, right? So there's a self-play loop here, right? And too many people are kind of focused on this idea of curating already existing data, where really I feel like people should be thinking about this idea of flow paradigms and, or as Andrew Ng calls it here, agentic flows, where you're using these LLMs to Socratically kind of analyze and compare each other's outputs in such a way that you're creating better and better quality data, and then that's really the self-play loop that's going to lead to the best possible model. And if I had to bet money, I bet you GPT-4v is trained on that, right? So GPT-4v has been the king of vision language models for a while now. Nobody's really been able to get close to them. And I think the secret sauce has been some kind of self-play loop, right? I bet you they're doing something very similar to what Andrew Ng is describing here, and something very similar to what NVIDIA is doing here, where they're basically using GPT-4v in combination with GPT-4, maybe multiple different types of GPT-4v that have been fine-tuned on different things, using it with a segment anything model, and then using that as a way to synthetically generate high-quality captions that you can then use to improve your original vision language model. So I'm pretty sure that this type of workflow to generate synthetic data to improve the model was already done, and that's why GPT-4v is better than pretty much every other vision language model. But now we finally have kind of an open source version of that, a paper version of that, because OpenAI isn't going to publish that work because they don't want people to know their secret sauce, but the secret sauce really isn't that complicated because deep learning really isn't that complicated. So here NVIDIA is kind of publishing what I think is the secret sauce to GPT-4v. Space Junk here repeating, what about KAN? KAN is Kolmogorov-Arnold networks. People are talking about this a lot. I thought about doing a stream on this. Kolmogorov-Arnold networks, but it just, I don't know, it's not that great. You know, there's a lot of hype and it's actually not that impressive. So like really what KANs are doing, I think the picture here explains it well. Oh, let me go back up. Is here you have a multi-layer perceptron, right? Multi-layer perceptron is your standard kind of deep learning architecture. It exists inside a transformer. There's a feed forward or MLP. Usually in any kind of classification or segmentation or something like that, usually at the very end you have an MLP as well. So model heads tend to be these MLPs, but MLPs are multiple layers, right? That's where the ML comes from. ML as in multiple layers, but ML also for machine learning. And each of these little neurons, right, has some weight, which modifies the signal that comes in, possibly some bias, although now the bias is kind of thrown away, right? Lots of MLPs don't have the bias term anymore. But you can see how all the neurons use the same activation function, right? So this is like a little GALU, right? Not quite a ReLU, but you can see it has that little dip. So it's a GALU or one of the little GALU variants. But a Kolmogorov-Arnold network is the same idea, except now you're basically parameterizing the activation function. So rather than your neural network parameters or weights defining the edge, right, you're basically parameterizing a spline. So here, let me go down to this. There's a picture here that I think makes it good. Yeah, so think about this. You have a function that is producing data, and then you're trying to train a neural network to approximate that function, right? So maybe some input x, input x and y, and then the output is this, right? So this is a very good problem for a KAN or a CAN, because this function that you're trying to approximate is composed of signs and a plus and a squared and an exponent. So if you feed this and try to train a KAN on this, it'll eventually figure that out, right? It'll eventually figure out that it's a combination of a sine plus a squared plus an exponent, right? And then what you're learning is effectively the parameters of this sine, the parameters of that exponent, and the parameters of that quadratic term. And then it'll figure it out for you. So here you go. EXP sine of pi x plus y squared. It figured it out. It's E y squared plus sine x, right? But here's the problem with this Kolmogorov-Arnold network is that it's probably not very efficient, right? If you read this paper, pretty much all the examples that they give are toy examples. So they only show that CANs are better than MLPs on these very specific toy examples, such as, right, finding these functions that are very specific, right? But the problem is that most machine learning problems that matter, such as image detection and stuff like that, are not like that, right? Like image detection is not some function that you can just recover, right? It's not that image detection can't be explained by that. So all the examples that they show, such as some kind of like knot theory in math and deriving some other physics equation, like, you know, that's cute, but like try to do image detection with this Kolmogorov-Arnold network, and I bet you it doesn't work that well. And another reason why it probably won't work super well is because it's going to be a bunch of different shit, right? So like MLPs work well because they're all kind of the same. You see how all of these activation functions are the same, and it's basically all of these neurons are the same, so you can do all the computation in a big batch, right? The reason deep learning has exploded is not because the architectures are cool, but because you can compute all the little, you can do all the computation in these big batches, right? These big matrices that run inside your GPU. But I don't know if you're going to be able to do that with these Kolmogorov-Arnold networks, because if you look at it, all of these are different, right? So if all of these are different, are you going to be able to do big, giant batch computation like you have with an MLP? Probably not, right? So I don't think they have the representational capacity to approximate more complicated functions, such as the semantic content of images or the semantic content of language, right? I think those are a little bit more complicated, and I think that they're a little bit too bespoke and weird, which means that when it actually comes to making these things huge and computing them in parallel, you're not going to be able to have the same type of efficiency as MLP. So that's my 2-minute summary of Kolmogorov-Arnold networks. Okay. Back to regular programming here. We're looking at this NVIDIA paper for the visual fact checker and how this agentic workflow can effectively be used to create higher quality captions even when you have lower quality models, right? So you're creating GPT-4 quality captions out of Llama 2, a segment anything model, a Lava captioner, a Blip captioner, right? So you're using these lower quality open source models to create a high quality caption. But what is a high quality caption, right? And now we're getting to the point of this paper that I think is the more important contribution of this paper, which is how do you evaluate the quality of a caption, right? Traditional metrics like clip score have served as a standard for measuring the alignment between generated captions and their corresponding images. Clip is a model originally from OpenAI that is contrastively trained with language and images, so it basically creates this shared embedding space where you can compare text and images. So you can take a caption, you can take an image, you can project them both down into this embedding space and then see how far away they are, right? So that's what they mean by clip score. But Clip image score, which is the new one that they're going to present in this paper, evaluates the similarity between the original image and the reconstructed version of the image generated by a fixed text-to-image model using the caption as a prompt. So this solves the problem that multiple correct captions may exist for a single image. All right, so what exactly is clip image score evaluation process? You start with your caption generation. An original image X is input into a captioning model, which generates a caption. This is either going to be your GPT-4V or it's going to be your workflow, right? So in this case, the captioning model is your kind of workflow that we just described. Then you're going to feed that caption into a text-to-image model. I think they mentioned Stable Diffusion XL, and then they also mention DALL-E 3, so they're using kind of the two go-to text-to-image models there. So you're going to use that caption to generate an image. Then you're going to take that reconstructed image, feed it into the clip image encoder, and get an encoded representation IX. So you're going to be comparing IX, which is going to be some vector, and you're going to be comparing that encoded representation with the encoded representation of the original image, right? So the encoded representations of the original and the reconstructed images are compared with cosine similarity. So here's your clip image score. Here's your standard cosine similarity. Here's a more verbose version of that. So in cosine similarity, you're basically taking two vectors here, which correspond to the embeddings coming out of the clip image embedding of your generated image and your original image, right? And you're just taking every element of that vector, multiplying them and summing them together, and then you're dividing it by the magnitude of those vectors, so taking every element of that vector, squaring it, summing them all together, square root, and this will give you the similarity score, right? So if this score is high, it means that these two vectors are basically very similar. They're pointing in the same direction, aka the point that they represent in the embedding space is very close, right? Clip image score turns a cross-modality comparison into a more intuitive comparison in the same image modality, right? So what they're talking about is that in the original clip score, you're actually doing a cross-modality comparison, right? You're taking the caption, it's producing some text embedding, and you're taking the image and it's producing some image embedding, and then you're comparing the text embedding with the image embedding, right? So that's technically a cross-modality comparison. Versus here in the clip image score, you're turning this into a same modality comparison, right? Because now you're doing a cosine similarity between an image embedding and another image embedding. And that's kind of fundamentally a better way of doing this, right? So maybe just to highlight exactly what that looks like, here you have an input image, right? So you take this input image, and then that's going to generate some caption. So you take that input image, you generate some caption. Then you take that caption and you generate images from it, right? So you feed that into a text image model, and it's going to generate some images. So you can tell how they kind of got some elements of it, right? It's like a kid reading a book on a bench, right? And then you're going to take those and caption those. So now you're going to take the generated images, caption them, and then compare those captions to the original caption, or compare the image embeddings to the original image embedding, right? So it's a same modality comparison, right? So you can see they're doing kind of the same thing here with the 3D, except in the case of 3D, you're taking the original 3D shape, aka just a 2D view of it, you're captioning that and then using that caption with a text to 3D model, which generates a 3D model from a text description, and then comparing those to the original one, right? So same modality comparison, which is the key part of that clip image score. Okay. So you have this new metric. How are you going to compare whether this new metric is any good? Well, that's what they're going to do in this paper. So they're going to be comparing different captioning methods, such as their visual fact checker to Lava 1.5, Blip 2, and they're going to be comparing clip score and clip image score. So if clip image score is a good metric, then it should generally agree with the other metrics, right? And that's kind of what we see, right? Cosmos and Lava are about the same for clip score, and Cosmos and Lava are about the same for clip image score. Visual fact checker has the highest clip score out of all of these. Visual fact checker also has the highest clip image score out of all of these. Okay, so these metrics are agreeing, but they're also both based on clips, so maybe that's not 100% what we want. Okay, well, what is the gold standard evaluation? Well, the gold standard evaluation is human evaluation, right? And this is what I always advocate for in these papers, is that you want a human evaluation to ultimately determine the quality, especially when you're doing text image generation, but in this case, caption evaluation. So for human evaluation, they're going to be using Amazon Mechanical Turk. They're going to be feeding captions compared to 5 other captions, and then using 3 different workers, and then majority voting for the final selection. And if you actually look at what you get out of that, you get a similar type of situation, right? So baseline versus VFC, this is kind of a head-to-head pairwise comparison, but we should see the human and the clip image score have the same, they should both have the same preferences, right? So here we see that VFC beats the baseline using clip image score, and then if you go to the human evaluation, you get the same situation, right? So humans seem to prefer VFC, and then according to the human evaluation rate, and clip image score, which is a much more more automated, right? This clip image score you can calculate without having to rely on humans, so it's going to be a lot faster. You're going to be able to do it even if you don't have the money for AMT, and it seems to be like it's a good metric, right? It agrees with human evaluation score, so it correlates with all of that, which means that maybe we should just be using that. right? And then it also agrees with GPT-4v. GPT-4v is very popular to use as a metric itself. Okay. That's pretty much this paper. Is there anything else interesting here? Yeah, this kind of shows you they take an image, they generate DALL-E 3 images based on the caption, and then they caption those generated DALL-E 3 images and then combine those into the visual fact checker. So pretty cool little explanations there. And that's pretty much it. All right. It's going to be expensive to get that clip score. Kind of. So Ed is bringing up the point that getting this clip image score is going to be expensive because you're generating images, right? So you have to pay for the inference to generate the caption. That's one inference that you're paying for. Then you have to generate or pay the inference for the text-to-image models. So if you're using 3 different text-to-image models, now you have to pay for the inference cost for 3 of those. So that's 3 more inferences. And then you're going to have to pay the inference cost of actually encoding those. So you're going to have to pay the inference cost for encoding each of those images and the original image. But I don't know, that's really not that expensive, right? You're talking about maybe less than 10 inferences per image. That I think that's still going to be cheaper than Amazon Mechanical Turk, right? And there's no human in the loop, which means that as image generation models get better, as our clip image encoders get better, as our captioning models get better, this evaluation metric will get better with them, right? So this is an evaluation metric that scores, doesn't have humans, and seems to correlate with human preferences. So I've actually changed my opinion, and I think that maybe clip image score is totally fine, and we shouldn't necessarily need to rely on Amazon Mechanical Turk as the gold standard. Maybe if we just use this, we can move research faster by having a more automated metric. Okay. Let's go to the next paper. So, evaluation, right? We're thinking about evaluation. We're thinking about how do you evaluate models. And another big conversation around evaluation is evaluating these language models on these benchmarks, right? So in this paper, Scale AI does some research and ultimately releases GSM1k. GSM1k is basically a new version of GSM8k, which has been the gold standard for measuring elementary mathematical reasoning. GSM8k was originally released by OpenAI. And the problem with using GSM8k is you have this leakage issue, right? Data leakage, or data set contamination. What happens is that when you rely on these public benchmarks like GSM8k, and what that means is that you can literally go and find all the answers for GSM8k, and not only are they available, but they're also sprinkled throughout the internet, right? So such benchmarks may inadvertently include examples that closely resemble the questions found in such benchmarks. Simply being able to repeat the correct answer that it previously encountered during pre or post training. So what's happening is that these benchmarks are woven into the internet, right? Maybe in some random Reddit comment thread that someone is training on, someone answered a question similar to this, right? So when you're doing that, the model is effectively just kind of memorizing the answer to that question, right? The model, in this case, these language models, they have such large capacity that they can effectively memorize, and even humans do this, right? Even as a human, when I was studying for things, there was a lot of times when on a test I was given a question and I didn't really even fundamentally understand how to do that question, but I remember there was a question on a worksheet that was very similar. So I just kind of regurgitate the answer on that worksheet and then kind of change the numbers a little bit, but I never really understood the question or generalized how to solve that problem, right? And as a human, you're less susceptible to this because humans don't have the same capacity that a large language model does, right? We have a much more lossy kind of brain. We have a limited capacity, so we generalize much more than we overfit. But these large language models, they have so much capacity that they're going to overfit much more. And the way that they prove that is that Scale AI creates GSM1k, which is basically a new GSM that has never existed out in the internet, so none of the models can overfit on it. And whenever they do this and they compare the performance, right, the gap between performance on GSM8k and GSM1k, they find something not good. What they find is that models like Mixtral and Phi, which are Phi is from Microsoft and then Mixtral is from Mistral, they perform a lot worse on GSM1k than they do on GSM8k, which means that their performance number on GSM8k is not indicative of true performance. What it's indicative of is basically overfitting, right? So this is a little bit of a naughty list, if you want to think of it that way, where they're basically calling out all these models here for being overfit to the benchmarks rather than having good performance just from a generalization standpoint. And you see here on the other side, you have the models that are good at generalizing and that aren't overfit. And unfortunately, it's GPT-4 and Claude, which are the closed source ones. So kind of sad for open source because all the open source models are on the naughty list and all the closed source models are on the good side of this. So GSM1k created solely with human annotators without assistance from any other LLM or synthetic data source. And maybe here it's a good point for me to make some enemies. So I'm going to make a little bit of enemies here, and I'm going to call out Scale AI. Right? So Scale AI is a company that basically annotates data, right? So they started off by annotating data for autonomous vehicles, right? So you basically have autonomous vehicles, they're recording a bunch of data with their cameras, and someone needs to go in and label that data, right? Create segmentation maps for that data, create object detection boundaries for that data. And that type of work is very grueling, and it sucks, and it's very low value, right? It's like if you want someone to annotate 10 million images, paying someone a US wage for that is extremely expensive. So Scale AI kind of emerged in the kind of early to mid 2010s as a company that did this for you. But what did they fundamentally do? What Scale AI fundamentally did was this. What Scale AI did is that they would connect you with these farms, right? So here you have, behind the AI boom, an army of overseas workers in digital sweatshops. So here you have Internet Cafe in the Philippines, right? So you have people sitting here in the Philippines, and someone in the Philippines labeling images, they're going to label images roughly about the same as someone in the US, right? But someone in the US, you're going to have to pay them whatever, $16 an hour. Versus someone in the Philippines, you can pay them $1 an hour, less than that, right? So Scale AI, they're trying to kind of greenwash and pretend that they're this awesome company, but really what they are is they're just a middleman that outsources labor to kind of second-tier countries, right? Like poorer countries where you can get people to do this for you. So that's not a great business, right? That's a very dirty business where you're basically just I'm sure they're not treating these people super well. I'm sure they're not giving them health insurance. It's not a good look. And if you want even more evidence that Scale AI is evil, here is Scale AI talking about defense. So Scale AI is doing all the data labeling for the Air Force and the U.S. Army, right? And what are we talking about here? Surface and subsurface detection, aerial object detection and avoidance. So that missile that's flying at a target and is doing some kind of object detection is running an object detection model that was trained on data that was annotated by people in the Philippines, all lubricated by Scale. So I don't know. I don't know about you guys. I might have made some enemies there. I don't know if any of you work for Scale AI, but like, to me, Scale AI is kind of an evil company, right? That's kind of the TLDR of my little rant there, is like, that these aren't good guys, you know? Like, they basically run these like farms, data farms, and then have absolutely zero qualms about doing all of the worst type of AI stuff, such as surveillance and reconnaissance and like working with the military for weapons. So, Scale AI, kind of evil. Kind of evil guys. All right. Created GSM1k. We do not intend to release GSM1k publicly. We plan on running recurrent evaluations of all major open and closed source releases and to continually update our results. When either the top open source models score over 95% or at the end of 2025, they'll release this publicly, right? And this is kind of important because you don't want to release this data set publicly, because once you release it publicly, then people are going to start scraping it. And once they start scraping it, it'll be in the data sets. And then once it's in the data sets, then you'll have the overfit issue, right? But there's also a problem with this, right? And the problem with this is that you're relying on Scale AI. Right, so here's Jim Fan. Academic benchmarks are losing their potency. Here's 3 types of LLM evaluations that matter. Privately held test sets, but publicly reported scores. Okay. Scale AI's latest GSM1k is a great example, but here's the problem. Trusted third party. Unbiased neutral party. Do these guys seem like unbiased to you? Right? Do these guys seem trustworthy to you? Right? Do you want to live in a world where your benchmark is a secret benchmark and the people who control that secret benchmark are funded by all the same VCs who own OpenAI and have Google shares and Meta shares and Microsoft shares, right? I don't know, you know, because like, how much do you trust Scale AI, right? Like, do you think Scale AI is going to say, yep, Llama 3 is better than Claude? Or do you think they're going to say, yeah, no, Claude is definitely better than Llama 3. Trust us. Right? Like, I'm sure they're not doing that now, but it's really setting them up with a lot of power here that is not necessarily great. Public comparative benchmarks like LMSys Chatbot Arena. I like this one better, right? This is kind of more akin to the human evaluation. So back to this one, right? Using human evaluators. But the problem is that this one is also not great because Jim Fan says you can't game democracy, but you totally can, right? If I really wanted my model to perform well, I could just pay for a bunch of people in the Philippines to go on LMSys Chatbot Arena and then just upvote my model, right? So all of these evaluations are all flawed in their own ways, right? Because you're either relying on this third party that is totally biased, or you're relying on these kind of arena scores, which you can game by just having people play to your favor. So evaluation is a very complicated problem, and I don't know what we're going to do, right? I think that, honestly, what these guys presented here, where you just have a metric that's based on language model, like, I think language models are less biased than a company and less biased than humans. So I kind of think that evaluation should be done by models themselves. I don't know. That's kind of where I'm leaning on this one. Okay. Let's learn a little bit more about GSM1k. So GSM1k is modeled primarily after GSM8k, which was released by OpenAI. It's common to remove all data with too high of an n-gram overlap with benchmark data. So what they're talking about here is the data contamination issue. So when people are preparing these data sets for pre-training, usually they're running some kind of embedding similarity, right? So they're feeding the text into some kind of model that is creating some kind of embedding. Then they're using something similar to this, right? Some kind of cosine similarity score, and saying, okay, if this data is too similar to GSM8k, it must mean that it's either someone talking about GSM8k or it's someone that copy-pasted GSM8k into some like blog post. So we're gonna pull that out, and we're not gonna put that in the pre-training data. All right. So this is things that people do to prevent data contamination issues. Okay. So there is some amount of prevention that is happening, but you're never going to get able to remove all of it, right? So GSM1k annotators were prompted with 3 example GSM8k and asked to produce novel problems of a similar difficulty level. So Scale AI doing what they do best. You know, they're literally the modern slavery farm. So if someone needs to write a new GSM1k, you know who's really good at that? Scale AI. Scale AI will hook you up. These guys were the guys who wrote GSM1k. Okay, all problem solutions are positive integers. We were required to send over the data sets via APIs. Our belief is that modern providers typically do not use such data points for model training. Okay, having an independent set of data annotators solve each question without seeing the intended solution. Reviewed by a special team within Scale responsible for conducting general quality audits for data production. Okay, so basically they have farms of these people, and then they have an internal team in San Francisco that, or maybe probably not even in San Francisco because that would be too expensive. They have some other farm of people checking the outputs of the original farm of people. Okay. Blah, blah, blah. They made sure that the answers are roughly around the same magnitude as GSM8k, right? They really want to recreate GSM8k, so they're like, the numbers need to be relatively small. When they presented human annotators with a set of 5 questions, 4 of which were randomly selected from the GSM8k dataset, annotators were able to correctly identify the lone GSM1k 21% of the time, which is pure chance. Okay, so basically they've proved that GSM1 is effectively the same as GSM8k. It's about the same difficulty. It's about the same order magnitude. The length of the questions is the same. And in every single dimension, it's pretty much the same as GSM8k, which is what they want. Okay. So for the evaluation, they find an interesting little situation here, right? Where here there's going to be 3 charts. The first chart is models that achieve a GSM8k accuracy of greater than 70%. The second chart is models with GSM8k accuracy between 40 and 70%, and then models with GSM8k accuracy less than 40%. Okay, so they're comparing 3 different tiers of model performance, right? So the models that are very good at GSM8k, aka the best performing models out there, you see kind of they're about as good on GSM1k as they are on GSM8k, right? So if you're on this line, it means that you're not overfit. If you're below this line, as most of these models are here, that means you're overfit. That means you're performing better on GSM8k, which is shotgunned on the internet, compared to GSM1k, which is secret inside the secret vault at Scale AI, right? So all these open source models, all these kind of middle of the road models are all overfit because they're all likely training on contaminated data sources, right? But if you're very shitty, right? So these are like the kind of shit tier models. These are kind of on the line too, which means that these are about as good on GSM8k as they are on GSM1k. So this actually kind of paints an interesting picture, right? Because it means that if your degree of overfitting is based on performance, right? Maybe there's something more than just data contamination going on, right? Some model families are systematically overfit, such as Phi and Mistral. Frontier models have sufficiently advanced reasoning capabilities so that they can generalize to new problems, even if they have already seen GSM8k problems in their training data set. And here's another way that Scale AI just kind of sounds evil and like makes me doesn't instill trust in me, is that they're introducing this new terminology, right? So if you noticed, when I described this, I talked about open source models and closed source models, right? So open and closed. Open is a positive adjective. Closed is a negative adjective, right? The closed source guys don't like that, right? They don't like being called the closed source guys because you're describing them negatively. So they're going to come up with new terminology for that. So now, this is the terminology. They're going to call it frontier models and not frontier models. Okay. So now these are frontier models, which sounds a hell of a lot cooler and better and more friendly than closed source models. And these are non-frontier models, which sounds a lot worse than open models. So The closed source AI is fighting back tooth and nail, and they don't want to be known as closed source AI. They want to be known as frontier AI, right? Because even though they're closed and secretive and they're not even telling you what they're doing, and ultimately they're probably doing a little bit of harm to humanity by being closed source, they want you to think of them as the good guys. So they're trying to relabel themselves as frontier models, which, I don't know, I think is a little bit disingenuous, but I'm obviously an open source zealot. Yeah, there's a lot of gaming with the term open as well. Yeah, there's even the open weight versus open source, right? People are really trying to mess with that terminology so that they get all the benefits and none of the negatives. Okay. But back to this weird relationship that we were looking at, where it seems like top performing models are not overfit and it's the middle tier models that are overfit. Overfitting on GSM8k is not purely due to data contamination, but rather may be thought of through other indirect means, such as model builders collecting data similar in nature to benchmarks or training on as training data, or selecting final model checkpoints based on performance on benchmarks. So this is more so kind of the classic overfit problem, right? So when you were training, when we have MNIST and CFAR and ImageNet, right, some of these classic benchmarks, the reason that we overfit to those over time is because we were doing kind of like a graduate student descent, right, where over time people were kind of selecting model architectures or picking the specific model checkpoint that performs best on those benchmarks. So that specific model is overfit in some kind of weird way to that benchmark, but not because it was trained on leaked data, right? So there's other ways that you can overfit to a benchmark rather than just kind of like training on the leaked data. And those were kind of the classic reasons why benchmarks such as CFAR and MNIST were overfit, but that's not really the exact reason that you're overfitting in this more modern language model context. In this case, we observe that the lemma models, here's a little typo for you guys. Ruh-roh. Typos in a public scale paper. Scale AI, why didn't you get these guys to read your paper and make sure there wasn't typos in it? Okay, we create GSM1k, a novel dataset designed to measure LLM overfitting on GSM8k. We find that several families of model, most notably the Mistral and Phi families, show consistent overfitting across all model sizes and versions. An extended analysis reveals a positive relationship between a model's likelihood of generating data points and its performance difference in GSM8k, suggesting evidence of data contamination. We find that frontier models exhibit little to no evidence of overfitting and that many models show strong signs of generalizable mathematical reasoning. So, yeah, they're not wrong. You know, like what they mention here, that this data is correct, but, you know, like it's really convenient that Mistral and Phi, Mistral is an open source model company, right? That's no good for Scale AI. Phi is a open source model trained on Microsoft that is pioneering the use of synthetic data, right? So Phi trains on a lot of synthetically curated and augmented data. That's not good for Scale AI, right? If you can synthetically generate data, then data labeling is a dead business, right? So who are all the Scale AI customers? Well, Scale AI, most of their customers are the closed source companies or the frontier model companies. So here's a paper coming out of Scale AI that really talks negatively about their biggest competitors and tries to relabel and spin their customers positively. So Scale AI is trying to do some tactical warfare on open source AI and trying to hit one for the team, for the closed source team. So a little bit disingenuous, but you know what? I'm going to take off my critic hat. At the end of the day, GSM1k seems like a good way of measuring performance, but I don't want Scale AI to be the unbiased neutral party that is trusted to tell us which model is better, because I think that they're going to end up telling you that the frontier models are better. Okay. What do you guys think of that? Money, money, money. Everywhere I see green. Like, look at this. Look at this. Look at this, like, all these closed source people. Eric Schmidt, dude, this guy is actually kind of evil. Like, he wants to basically make it illegal to train open source models, and anybody who uses a GPU in the cloud needs to give them your driver's license. I don't think Greg is evil, but I think he just kind of sits there and lets people do evil things on his behalf. Right? So, if you're just sitting there and letting other people do evil things around you, are you evil or not? I don't know. I've made all the enemies, dude. Like, no one's going to give me any money because all these VCs are friends. Feifei is also not evil. She's not evil in the way that Greg isn't evil, though. I think it's like she's not individually evil, but she's sitting there and giving talks at all these closed source companies and kind of like being part of regulatory boards and kind of rubber stamping. So it's like people like, it's like you, if you're not evil, but if you're giving technical credence to the people who do the evil decisions, right? If you're there kind of nodding your head as people are doing evil things, are you evil? I don't know. That's a very complicated moral question that I don't necessarily have the background to answer, but are they culpable or not? Evil adjacent. That's a good way of putting it. All right. These papers were pretty short. That's pretty much all of it. I realize we've only done an hour here, but you know, I've been trying to do a little bit shorter streams. I have a little bit of work to do. You know, I've kind of been ramping up the work, so I don't have enough time to really dive deep on all these papers anymore. So I figured doing shorter streams with easier papers is probably a way to solve that. So I'm probably just going to go into the summary. If you guys have any questions, you can ask them. If not, I'm going to summarize this stream and give you guys back some time. All right. Question from Christopher. The Arnold Kolmogorov thing is meant to be replace the whole MLP. Maybe the idea is just to learn an activation function. Yeah, I think if you really like, the one thing I would love to see is for someone to take a transformer, right? Like, let's go back to our BBY Croft, this visualization. So this is a nano GPT visualization. This part right here, the attention mechanism, you're not going to replace that with the KAN, but this part here, this is an MLP, right? So this feed forward part is an MLP. So you could probably take transformer and replace the MLP with this Kolmogorov-Arnold network and see if it does something, right? Like, does it even work? Is it about the same quality, or is it way worse? And then beyond quality, how much more compute heavy is it, right? Like, when you actually try to train a KAN inside a transformer like this, does it completely screw up your training pipeline? When you do inference, how does it work there, right? Is it efficient at inference? Is it not efficient at inference? Does it take more memory, less memory? So a lot of these questions still need to be answered, right? And this paper doesn't answer them, right? All it does is just give you like some bogus toy problems, and it's like, okay, well, that's not really applicable, right? So I don't know. We still need to see. But could be good. I would say if I had to bet money, I feel like this is going to go the same way as capsule networks or any of these other kind of like weird bespoke model architectures. Ultimately, they're not going to perform as well as your basic stuff, just simply because the comparison here isn't being done with compute equivalence, right? It's like if you said, okay, an MLP that takes the same amount of compute as a KAN, the MLP is going to be bigger, and thus the bigger MLP is going to have more representational capacity than a smaller KAN even if the KAN of the same size would have more representational capacity, right? So like you can't compare these things like this. You have to compare them from the lens of how much compute does it take to run this versus this. And also try it on some harder problems. All right, let's summarize. So today we had a nice little short, cozy Saturday stream where we were looking at evaluation and 2 different papers on evaluation. First paper we looked at is this NVIDIA paper called Visual Fact Checker, where they create a workflow or a flow engineering way of creating high quality captions for images, right? So they basically train, or they don't train at all. There's no training here, right? This is a training-free pipeline, as they describe. Training-free pipeline, where they get captions out of images, image captioning or 3D image captioning, which is just image captioning, but you're running it on multiple views of a 3D thing, that is on par with GPT-4v. And the way that they do that is with this flow where they have worse captioning models, open source things like Lava and Blip. They feed that into a large language model, which then kind of goes back and forth with a open vocabulary detection model, or goes back and forth with a visual question answering model. And this refining eventually creates better captions, right? And that's pretty good, right? Because it means that you can use shittier models to generate higher quality data. And ultimately, this type of Socratic method is going to be the reason or the method that we get to artificial superintelligence, right? It's a self-play loop or a kind of a data generation technique that, as Andrew Ng puts here, results in higher quality output than, in this case, the VLM can generate directly, so that then you can train on that output to become even stronger, right? Which I'm pretty sure is what GPT-4 Vision did, right? Is they created some kind of self-play loop like this. So, okay, pretty cool. But the other part of this paper that I think is also important is this new metric that they introduced called the clip image score. This clip image score is a metric which allows you to evaluate how good a caption is with a image, but rather than just using the clip text encoder and the clip image encoder and then comparing those with cosine similarity, in this case, you're going to be using the clip image encoder with the original image, and then the clip image encoder with generated images based on the caption of the original image. And this allows you to basically compare embedding vectors that come from the same image encoder and from the same and are in the same modality. So it's going to be a little bit better of a score than just clip score. And then, not only do they introduce this new metric, but they go to show you that this metric agrees with clip score, and it agrees, more importantly, with human evaluation, right? And this is, human evaluation is the gold standard for determining quality, right? Something like chatbot arena is fundamentally coming from the intelligence of the human evaluation, right? Your chatbot arena is a good benchmark because humans are the ones doing the evaluation. But if we now have automated evaluation metrics that you can do without relying on AMT or some kind of decentralized group of people like the chatbot arena, then you're going to be able to evaluate these things inside training loops or evaluate them automatically, which means that you as a researcher won't have to pay for AMT. So I think this type of automated evaluation unlocks research and future kind of synthetic generation techniques in a way that's pretty powerful. So yeah, even though low-key this paper was just about this flow, I think that the real story in this paper is that you can create an automated evaluation without a human in the loop that agrees with GPT-4v evaluations and AMT or human evaluations. All right. Then we went from talking about evaluations of vision language models to evaluations of large language models. So in large language models, you're evaluating with these public benchmarks, such as GSM1k, but these public benchmarks, they've been around long enough that they've started leaking into the internet, right? So people talk about these on blogs and threads. People post questions from these on blogs and threads, and whenever people are scraping these data sets to do pre-training on, even if they're doing some data set filtering, where they're looking at the embeddings and making sure that it's not literally GSM8k as in your training data set, it's still leaking in there, right? And because it leaks in there, it means that you're overfitting. So your model isn't actually good at grade school math. What it really is your model just has a huge amount of capacity because it's a large language model and it can basically memorize everything. And it's kind of just memorize the answer to these things rather than actually being able to reason and actually give you the answer to this problem, which is the whole point of GSM8k, is to evaluate your ability to solve elementary math problems. So data leakage is a thing. Scale AI basically got a bunch of people to create their own secret version of GSM8k called GSM1k. So they had a bunch of people create questions and then answer those questions and then go through their whole kind of like data cleanliness pipeline. And yeah, that's it. But this whole paper just just reeks a little bit of I don't want to say evil, but I want to say open versus closed AI war, right? So there's a war happening in the AI world right now between the open source models and the closed source models. And Scale AI is a warrior for the closed source models, right? Scale AI is basically funded by all the VCs who own all the stock and all the stuff in Google and Microsoft. So these guys want closed source AI to win, right? And Scale AI is really good at basically getting people in the Philippines to do your stuff for you, because people in the Philippines, you don't have to do health insurance, you don't have to pay them anything, you can just fire them whenever you want, right? You don't have to worry about anything. You pay them literally nothing, and it's a great way to get people to label stuff for you, and they can label a bunch of sketchy shit, such as battling and missile guidance systems and all this kind of weird defense crap that other people might be too scared to approach. But Scale AI does not get afraid of that. Scale AI wants closed source AI to win, so they're basically relabeling, and rather than saying closed source AI and open source AI, they're now calling it frontier AI and not frontier AI. So they're shooting cannons at Mistral and Phi, which are the open source AI, and yeah, I don't know, a little bit sad. But Scale AI positioning themselves nicely as this neutral third party, even though they're not neutral, and they're going to be running the benchmarks for you. So they're going to tell you which model is good and which model is bad, right? They're going to be the kingmaker. They're going to be the ones that say, okay, we've done some internal testing and Claude is better than Llama 4. And you're like, okay, can I see that internal testing? And they're like, no internal testing for you. You can't tell what our data set is. You just have to trust us. So that's a lot of power to give people that have a history of being a little bit sketchy. But IDK, I'm sure they have the best intentions. I'm just a guy on the internet. I don't actually know what's going on in Scale AI. So take everything I say with a grain of salt. Hoopo will inspire and lead broadcast open source guys to victory. I don't know, hopefully. Or not. Or I get arrested for promoting dangerous ideas like open source AI. One of those two. Anyway, that's all I got for you guys. Thanks, MW87GM, Check B Khaled, Ed, Max Callie, Christopher Every Dream, Snooks, who else? Space Jank, Yang Wang, Max Malley, Lil Kim, Christopher M, Ishan, 2ARX, and Sarah. Thanks everybody for listening. Hope you thought of some interesting things. Hope this made you think about things and think about evaluation and think about what type of world you want to live in. And once you're done doing that, because that's going to be quite of a heavy thing to think about, maybe join us tomorrow. Tomorrow we're going to be looking at Gaussian circles, which is kind of a new, interesting variant of Gaussian splats that has a couple people excited, and we're going to kind of check it down, deep dive, see if there's something here or whether this is just some other kind of random niche sideshow situation that's just going to end up forgotten, much like Kolmogorov-Arnold networks. That's all I got for you guys. Thanks. See you guys later.